All right, 5.2 is on power functions and polynomial functions. Power functions are functions that have this form, f of x equals kx to the p, where k and p are both real numbers. K is called the coefficient, and p is the exponent. So I've got three sets of examples here, some obvious examples, some less obvious examples, and some non-examples. So the obvious examples, yeah, we've just got, coefficient times x to a power. And same thing going on in all of these. This one over here is maybe a little different because it's got r instead of x, but it's still a power function. These that I said are less obvious. It's because they have negative or fractional or other powers. Like this one is x to the negative 1. This one's x to the half. This one's 2x to the negative 2. And this one over here is 4x to the 0. So those are also considered power functions, although for the most part in this section, we're really going to look at power functions where the exponent's a whole number. But these still qualify as power functions. Now these guys in the non-examples don't. Let's see. This one doesn't because it's an exponential function. X is not the base. X here is the exponent. This one's not a power function because you can't rewrite it as x to some power. You could rewrite it as x squared plus 1 to the negative 1, but it's still not just plain old x raised to a power, so not a power function. Logarithms are not power functions, and this is pretty much the same as this one over here. Not a power function. So the next thing I want to talk about is their end behavior. And I'm really being a little more specific here. Instead of just all power functions, end behavior of power functions with positive integer exponents. So, if we're given some random, like down here, I'm asking about what's the end behavior of these different functions. It turns out, to answer for any of these, all we really need to know about is the coefficient and whether the power there is even or odd. So really all we need is to know 4 graphs. I'm going to do these in purple. Y equals x squared looks like this. So what we would say is, as x goes to infinity, y also goes to infinity. What that means is, if we trace along the function from left to right, as we go toward infinity, so the further out I go in this direction, this is going to get me going higher and higher. So as x grows large and positive, y also grows large and positive. Now we'd also say as x goes to negative infinity, so that means if we're going the other direction, if we're tracing along the function and we're going further and further to the left, we're still going up. So y is also going to positive infinity. That's the formal way of writing this out. You can also say this for your end behavior. The book is going to use the infinities there, but just showing that both ends go up, that gets the point across. Now for negative x squared, both ends are going to go down because you're going to have a parabola that goes down in both directions. So this one, as x goes to infinity, y goes to negative infinity. And as x goes to negative infinity, y goes to negative infinity. All right, y equals x cubed looks like this. So in case it's not clear, think about the real number line here as having infinity on this end and negative infinity on this end. Of course, there's not an end to the number line, but think of going forever in the positive direction as going to positive infinity, and forever in the negative direction to go to negative infinity. So in this guy, when we go toward positive infinity and follow along the function, we're going up. So as x goes to positive infinity, y goes to positive infinity. And as x goes to negative infinity, y goes to negative infinity. And then y equals negative x cubed looks like this. So as we go further to the right, to positive infinity, the y value approaches negative infinity. And as x goes to negative infinity, y goes to positive infinity. Now you can also sum this up by saying over here, that tells the end behavior there. This tells the end behavior here. And this tells the end behavior here. All right. Now, I think this makes good sense because if you look at a graph like this, like x squared, both ends go up. If I change that to x to the 4th or x to the 6th or x to the 8th or x to the 48th, they go up faster and faster. So all of these, the end on both ends, they go up. If I put a negative on front of that, it makes both ends go down. And if I put a coefficient in there, it just makes it go down faster. Well, if I put a big coefficient in there. If I put in a coefficient like that, it goes down slower. Although with x to the 48th, it doesn't really matter. It's still really fast. If I put in x cubed, notice it's going down on one side and up on the other. And that's the same if I put in any other odd number for my exponent. Notice it gets flatter, but it's still going down on one side, up on the other. If I put a negative in the front, it's going to change the direction. So basically, if you know the sign and you know whether this is positive or negative, or I'm sorry, even or odd, that'll tell you everything you need to know about the end behavior. So let's look back at this. Determine the end behavior of the following. Negative 2x cubed. The fact that it's negative and x cubed means it's going to act like x cubed. And I should actually put some dots in the middle, because we don't, well, this particular function would look like that, but we don't always know. 3x to the 5th, this is positive. 5 is odd, so it's going to behave just like x cubed. And negative 2x to the 8th even means that both ends are going to go the same direction. Negative means they're going to go down, so this is going to act just like minus x squared. And if we wanted to, we could write this out using the more formal notation, but that's what the ends do. All right, we'll stop here and we'll pick up with polynomials on the next video.